So the last, oh, not the last, sorry. We have one other lesson in this chapter. It's really short chapter, which is kind of nice. So we have composition of functions, which we'll deal with today and tomorrow, or not, yeah, today and tomorrow. And then we have inverses, which we'll deal with Thursday and Friday. Next week, we will review, and then on Monday, and then on Tuesday, Wednesday, and Thursday, you'll have time to work on the chapter quiz just on this lesson, the arithmetic combinations, composition, and inverses. So that's kind of what's going on and where we're headed. Let's take a look at compositions today. So I know we've done compositions in the past, or you have in other courses. And they can be written one of three ways. And to be honest, I've never seen the third way, which is kind of interesting. But the first way, we have f and then in parentheses g of x. And then there's that circle notation, f circle g. It's actually read f composed with g of x. And then this third way with arrows. So y, arrow g, arrow f. And the only thing that I can figure is your y value comes from plugging into g and then plugging into f. I'm not sure exactly the history of that notation. So I generally don't use this one, but I have used the other two and use them frequently. For the domain, it's again a little bit different. So the domain of the composition of f with g is all values of x such that g of x is in the domain of f of x. And we'll take a look at it with examples because I think the definition by itself is pretty difficult to understand. But once you see it in practice, it should hopefully make a lot of sense. All right, so again, similar to the end of last week, we're just going to look at a pair of functions, find the composition, and state the domain. And the order does matter. So it's f composed with g. So we're going to take g of x and plug it into f. So pretty unusual with the composition. You actually work from right to left instead of left to right. All right. So f of g, f circle g of x. Actually, I kind of like that my computer puts it almost like a superscript. Makes it a little bit easier to deal with, I think. So we're going to take 2x minus 1 and put that in for x. And I would prefer to multiply that out. So again, depending upon which method you like, we have the box method, we have the FOIL method. I think I did FOIL with everything last week, so I'll do the box method with this one just to refresh our memory. So 2x minus 1 times 2x minus 1. Two x times 2x is 4x squared. Whoops. That's really bad. 2x times minus 1 is negative 2x. Negative 1 times 2x is negative 2x. And negative 1 times negative 1 is positive 1. Combining our negative 2x and negative 2x, we get negative 4x. So plugging that in, 4x squared minus 4x plus 1 plus 3. And I'll be honest, I really didn't try to do this, but the fact that it's 4x squared plus 4 minus 4x plus 4, just all fours is just kind of a happy coincidence. For the domain, again, if we have roots or rational functions, we need to be concerned with what values we can plug in for x. Because these are both polynomials, there are no restrictions, and the domain would be all real numbers. Again, a couple different ways you can write that. Interval notation, or the fancy R, either one works. All right. The second one looks a lot easier, but it's not. I think finding the composition is pretty easy. F composed with G of X. So again, we're going to take this square root, plug it in for X. And if you watch the video from last Friday, we don't need to rationalize that. If you remember from probably algebra 3, maybe you did rationalizing. We may do some more later in the year, but you can leave it just like that. Now we need to look at the domain. And if we look first at G, we know that the square root of X, in order to take the square root, X has to be greater than or equal to 0. And if we look at F, we can't have 0 plugged in to F. So our domain all X such that, and we're just going to combine these two things. So X is greater than or equal to 0, but not equal to 0 can be written as X just has to be greater than 0. That's a really bad bracket. Wow, that's so much better. So there is our answer. All right. Now the fun ones. All right, so we have f of x is a fraction or a rational function, x plus 1 over x minus 3, and g of x is x minus 2 over x plus 1. So we'll do f composed with g. And we're going to take this whole fraction and plug it in for x. Now, this is one that I would recommend simplifying. All right. So in that top fraction, I would have a common denominator of x plus 1. And the nice thing is that second value there, that plus 1 here, can be written as x plus 1 over x plus 1. In the denominator, x minus 2 over x plus 1. So we get that. Now I'm going to write it as a single fraction in the numerator, a single fraction in the denominator. So x minus 2 plus x plus 1 over x plus 1. And x minus 2. Be careful with this subtraction. It gets distributed all the way through. And what do we get? Negative 2x minus 5 over x plus 1. Whew. Are we having fun yet? Now, the last step, think about this as a division problem. So it's divided by negative 2x minus 5 over x plus 1. And then we can use our rules for division of fractions. And we have that common factor of x plus 1 that cancels out. Whew. Now we need to think about the domain. And I'm going to go all the way back up to my original expression. So for G, the only value that we cannot have is -1. For F, the only value we cannot have for X is 3. But remember, that value of 3 would come from G. So what we want to do is find where X minus 2 over X plus 1 is equal to 3. Or technically, we want it to not be equal to 3. So I would think of that as 3 over 1 and cross multiply. Question, or we got it? Now solve for X. I would probably subtract X from both sides. Subtract 3 from both sides. And I get X cannot be -5/2. And I think when we, so -1 and -5/2 would be restricted from our domain. And I think what you'll see is the -5/2 would make the result of our composition 0. So again, in set builder notation, all X such that X is not -1 or -5/2. So on page 458, problem set 65A, you're going to do 1 through 15. And they're just like the examples that we had of finding the composition and stating the domain.